This is problem 3 from the fall 2010 exam. So it says, below are shown 4 charges arranged in a square centered at the origin. They all have a magnitude of 1 microcoulomb, but the charges have different signs. And we're supposed to draw the electric field vectors as arrows at the points indicated by X's. The arrows should point in the direction of the electric field. If the field is 0 at a particular point, write E equals 0 at the X. Okay, so to do this, we want to imagine that we have a positive test charge, and we'll put it at each of these arrows, and our electric field will point in the direction that this positive test charge will go, so toward the net, in the direction of the net force on that charge. So let's just pick a point, and say we put a positive test charge here at the origin. It would be repelled from each of these positive charges, so we'd have 2 force vectors like this, which would cancel. And it would be attracted to each of these negative charges, and those will be in equal and opposite directions. So the net force on this positive charge would be 0. If we pick, say, a point like here, then it would be attracted toward this one and repelled from this one, and so those 2 vectors would look like this. Those will cancel and add up to something just net in the y direction, and these 2, the same sort of thing will happen. So we'll have, it would be repelled from this one and attracted to this one. The x components of those 2 will cancel, since those will be equal but in opposite directions, and the y component will be a net in this direction but will be smaller than the effect of these 2, and so the net effect is still something that will point up. You can make the same arguments for this point out here, except for it'll be a little bit smaller. So we have a 0 here, large up here, and up here, and the same sort of arguments for over here, so except for down. So now these points up here, if we chose this one, it would have to, it's similar arguments to these. So in this case, though, we're going to get something that points in this direction. So away from this one, towards this one, and the effect of down here is going to be towards this one and away from this charge, but these 2 will have a smaller effect than these 2, and the net result will be in this direction. If we choose this point here, we're going to be attracted along this line and repelled from these 2, but this is the closest, and the net result will be in this direction, so directly toward this one along this line. And over here, a similar argument, except for this is, so the effects of these 2 will cancel in the component along this direction, and we'll get something that's pointing away like this. And these 2 points, these last 2 points, are the trickiest of them, because it actually depends kind of on exactly where these are. But to think about it, the easiest way to think about it is like if you had, so you have one of these 2 dipoles, and the electric field vectors due to each of these does something like this if you just have a single electric dipole. And so along this line, it'll always point this way. And along this 45-degree line, it'll always point away. And will always point up along this x-axis. So at some point in here, some arbitrary point, it'll be some value like this. So if I had drawn those lines on here, they're going to point from the positive and toward the negative. So we'd have something like this. And at this point here, it's going to point up a little bit. It's actually kind of close to the point where it points inward though. But this point will be slightly up. And so the effect of this dipole is something that's basically in the opposite direction, so it'll make this smaller, but it'll still point up just a little bit and inward. So, okay, and then over here you'll have something that points, by a similar argument, will point down just a little bit since it's closest to this dipole, whose electric field lines will go like this. So it'll point down and to the left. Okay. So those are, now we have all of our electric field lines, and we want to do this part B. So sketch the electric potential as a function of x position along the dotted line shown in the figure above. Use a reference potential V at infinity as 0. So now we want to take our test charge and move it start out at V at infinity and move it along this line in this way. And the net work we do to get to any point along this line is going to be the potential at that point. So we'll start out at x equals infinity, and we'll be way out here, and we'll be 0 at that point. So V at infinity is equal to 0. And then as we move it in, at whatever work we've done, we'll plot here, and that will just be our potential. So along this line, you can see that the y component we don't care about, since that'll always be perpendicular to our motion along this line. So the only thing we care about is the x components of each of these things. So you only care about the component of the force that you need to apply in the direction that you're moving. So all of these, the electric field along this line have components that point in the, except for this one right here actually, but they'll point in the negative x direction for all these points out here. So our test particle will be pulled in that direction, and so as we move in this direction, we're going to have to apply it. So this is our displacement vector. We'll have to apply a force to counter the field in this direction. So we're going to apply a force in the positive x direction as we move this way out from V infinity. And so we're going to be doing negative work as we go out here in. And as we get closer and closer to here, we'll keep doing more and more negative work. This point, though, our work will be 0, since you can imagine that we could come from some point out at infinity along down this line, and we'll always have a perpendicular, the force will always be perpendicular to our motion in that case. And so it could come here, and we'd end up with a 0 potential at this point. And so now if we know that we have to have a 0 potential here and a 0 potential out at infinity, and since if we come in this way, the work we've done gets more and more negative, since our force is always in the opposite direction that we're moving. So we get something that comes down this way, gets more and more negative, and will eventually come back up as you have some, in this region you have large electric fields pointing this way. Okay, in this direction though, we could have come from negative infinity and then moved our test particle this way. And so in this case, the electric field points in this direction this whole way, and so we're going to need to apply a force in the positive x direction in order to counter those fields. So we're applying a force in the positive x direction and moving in the positive x direction. So as we bring in our particle, we're going to be doing positive work. So that means that if we start out here at a 0 potential and come in, as we get closer and closer, we're going to be doing more and more positive work until some point when we get towards here and the electric field vector flips towards this direction. And then when that happens, then we're going to need to apply a force in this direction to counter it. And we'll be moving still in the positive x direction, applying a force in the negative x direction, and be doing negative work. And so the work starts to decrease again, or the potential will decrease again. So overall, you'll get something like this. So 0 at infinity, 0 at negative infinity, 0 at x equals 0, and positive on this side, negative on this side. Okay, for part C it says, is the work you must do to move a +1 microcoulomb charge from the x labeled A to the x labeled B positive, negative, or 0? Circle the correct answer and explain. So we're moving from A at the origin here to B, this point here. So at A, the potential is 0, since the contribution to the potential to these 2 positive point charges and these 2 negative point charges cancel. They're all equally distant from the origin. So the potential at the origin is 0. And the potential here, we found already, was some negative value. And so we're moving from 0 potential to some negative value if we go from here to here. And so the change from A to B will be negative. And so we're moving from V equals 0 at the origin to V is V less than 0 as found in part B.